So now that we've seen a variety of ways to install SUSE Linux, let's take a look at some basic, what we'd call Unix Linux usability commands, basic skills. So we'll spend a few sections covering critical commands that'll help you to navigate Linux-based systems. Of course, not only SUSE, but any distribution for that matter. So these are just cross-platform, cross-distro basic Linux skills. So let's talk about these. So basically, to summarize, these particular utilities, let's say, facilitate, let's say, relatively easy navigation and usage of Linux systems in a nutshell. And we like to present these tools in no particular order, just perhaps in some sort of logical order in how you may actually approach them from the shell, but in no particular order of importance. So, explore tools. And let's say this is A, and the first tool we'll look at numerically. So, what happens when you open the shell? That's where we like to begin. You open a new shell, such as the first instance. We'll close these instances, for example. So can those, this is the first shell that was opened, and we launched the gedit application from it. So by invoking a new shell, essentially a pseudo terminal or PTS device is instantiated, and it lives within the context of the permissions, the effective permissions of the currently logged in user. So let's say spawning a new shell generates a new, let's say, pseudo terminal or PTS device. So pseudo terminal PTS device. And this obviously means it's in the dev tree. So for example, dev PTS and some number 0 through n. Now let's take a look here. Let's just finish the single quotes to see what happens. So the pseudo terminals are indexed at 0. So the first shell you open for the first connected user, since we're the lone connected users to the system, spawns pseudo terminal shell 0. So that's this shell. So that means if you subsequently generate another shell, it'll be incremented usually by 1. Sometimes it's randomly generated. Sometimes the numbers will be off because other users are using the system simultaneously. So by spawning this new shell, we can tell what shell we're connected to by executing the tty command. So this reveals pseudo terminal 1, and subsequent invocations will reveal accordingly 2, 3, and so on. And as you close shells, those devices are returned to the kernel's space for further reallocation or further allocation by subsequent users. So for example, if you take a look at dev PTS, you'll see the ones that are currently open. And it's a multiplexer, which means for each incoming connection, it spawns as many as necessary, just as is the case with TCP/IP-based connections. And as we close them, dev PTS, the instances are closed. So now we have 0, 1, and 2, and so on. LSL, dev PTS, now it's just 0 and 1. So the spawning of pseudo terminals is facilitated by the kernel in conjunction with GNOME to present it to us graphically, or the programs that give us shell access such as SSH, etc. So let's just note that. Let's say the shell providing program works with the kernel to supply shell or PTS device. And those programs include SSH, Telnet, as well as GNOME terminal. And any sort of terminal generating application. And the application that helps you to determine the currently connected pseudo terminal is TTY. So reveals currently connected TTY. And this applies, of course, to actual TTYs or console-based TTYs. So note applies to console-based TTYs as well, for which we have, let's say, IE TTYs 1 through 7, with 7 usually affixed to the GUI, which is what we tend to navigate through when we install as well as use the system in general. So TTY is an important command to know which shell to which you're connected. Now, there are a host of other commands that will reveal information about your current login status, so let's just go through them. So, you have a new shell, you know the TTY to which you're attached, but who are you? So who am I reveals per shell, or let's say per TTY effective permissions. So let's take a look here. Who am I? Well, in this particular shell, I'm the user Linux CVT. Perhaps, however, in a separate shell, I've elevated my privileges and I'm now this user called root. So it is on a per shell basis. Every shell invokes a process. In the case of SUSE Linux and other distros, that process is bash. And then from there, subsequent child processes are attached. Who am I explains who you are in a particular shell. You're either the privileged user root or a non-privileged user. However, you can be anyone in any shell. The shells are entirely unrelated. So who am I gives us that information. Let's just note that shells attached to TTYs are independent. So they do behave independently. And if you PS in any shell, which is another important command, you'll see for that particular shell, the primary process attached to its pseudo terminal. Well, you'll always see the pseudo terminals wherever applicable. Some processes are not attached, but wherever applicable, you'll see it. So in this particular shell, bash was executed and followed by SU, then PS. How do we know that's the order? Well, if you look at the PIDs usually increment upwards. So this particular PID was called after an SU. So we SU'd in successfully, 69. A bash instance was launched, and then subsequently we launched the PS process. So you get who am I information on a per shell basis. Now that you know you can figure out who you are and to which shell you're attached, what about other users in the system? So W, for example, reveals connected users to various TTYs. So from a shell, if you execute W, you'll see the different users and their shells, and their consoles or TTYs or access points, if you will. So if SSH, then it'll be a pseudo terminal. If GNOME terminal or KDE or any graphical terminal, it'll be a pseudo terminal. If at the console, it'll read console. If it's a physical TTY, such as 1 through 7, it'll reflect accordingly. So currently, these are the connected instances or users to the different pseudo terminals. And as you can see, we dominate all of the terminals because we're the only user using the system. Even in this shell, this current window, which is pseudo terminal 2, the rightful owner is actually Linux CVT, who then spawned the SU process, and then that invoked bash, and then we executed something such as PS or what have you. So W reveals that information, and it can be useful in that regard. Now, when you're within the shell, how do you move around? How do you know what's in a given directory? Well, a series of commands, basic commands, are there to help you. So pwd tells you where you are within a directory space. So reveals current working directory. And this is, of course, relative to the root file system, as all things are in Nix. So pwd, where are we? Well, relative to the absolute root of the file system, which is just /, we're a few levels down in home, Linux CBT, desktop. Now the prompt reveals that information. It's configured to do so. Sometimes it loses this information, and on some systems, it may not be configured yet on other systems. You may be so deep into a particular tree that it isn't accurately represented on the prompt. In other words, there are limits to how much information may be displayed on the prompt. So if you want to absolutely know where you are within a directory tree, execute pwd, and that'll tell you where you are. Now to examine the contents of a directory, ls, with its myriad options. So we open a shell. Where are you? Well, let's draw back. We don't need to be in its root for now. So we know we're in home Linux CVT desktop in this particular case. But what's in the directory? ls gives us that information. Now notice nothing shows up. ls by default does not display hidden entries. The A option will reveal those hidden entries. If there's truly nothing in the directory, then you'll just see the standard ... So ls has myriad options, but the key ones include lsa, reveals hidden entries, and let's just know IE dot, which is just CWD, current working directory, and ... is just one level up. LSL, long format, returns ownership, permissions, timestamp, and inode data. So this is perhaps the most useful option, L. But if the directory is truly empty, nothing will be revealed. So we move one level up and we LSL. And there you see permissions, link information, ownership information, modification information. Let's just drop the inode information. This is if you include the I option. So similarly, LSLI, all of above plus inode data. So that can be useful as well. Sometimes you just want to know which inodes are associated with which files and so on. So that returns the inode data. So ls gives you that information. ls, of course, can take as its argument any directory you pointed to which you have permissions to read. So for example, lsl, etc, and you'll see the contents of etc. lsl, etc, as well as var will show you the contents of both etc and var. lsl one level up shows you one level up, and so on. LSL, a directory relative to our current directory, or ls, any of the ls options, any directory relative to anywhere that we have access to, it'll reveal the contents of that space. So that's also a useful command. Another one, so now you've been using your system for a long time and there's all sorts of content across the different directories, namely your home directory, because that's where we normally operate from. But you're just not sure which directory, where it's buried, so on and so forth. So how do you find it? The find command helps you to do that. So let's say, for example, you're looking for files that end with text. You can do a find from the current directory or give it some sort of index, such as home, your home directory, or etc, or var, or elsewhere. Then use the name option, and there are many other options, many other ways to search, such as by inodes, by executable, by basically any metadata associated with files. But perhaps the simplest search is to use the name option. You know you're looking for something that has text in it. So this is one way to search. And this will search current directory, and it automatically descends through the hierarchy in search of your content. So here we are. In our current directory, we're looking for something that has text, actually our quotes. We have two different types of quotes going here. Let's use single quotes alone. So we're looking for star text. However, our two files don't have text, the original file plus the backup. So let's say we know it has something to do with notes. So this will find it. And if you think there are a variety, then just use the wildcard and it'll search it. And it could be anywhere. So let's say you were outside of the directory, you just want to search from home. Well, this will search where you have permissions to do so in home, and ultimately return the full paths to those content for you. So star text, star descends the tree from the current location, or let's say from the CWD, to find content. And find can search any metadata. So let's say find can search based on any metadata associated with files. So that's just a simple example, but just know that find's there, it's available, and it helps you to get or find content. Another important utility that we reference in scripts a lot is touch. So this creates or updates file timestamp data. So if file doesn't exist, then it creates an empty file. So for example, touch test.txt creates an empty file. Let's say if not exists, or updates timestamp. So let's take a look. Let's operate outside of our documents directory. In fact, just to separate, let's make a temp directory and operate from there. That's what we tend to do. So touch test.txt. Well, if the file doesn't exist, it creates an empty file. And if it does exist, it simply updates the timestamp, modification timestamp associated with the file. So we'll allow some time to elapse so we can compare and contrast, at least into the 3rd minute of the 8th hour. Why is this important? Sometimes, as part of a routine, as part of a script, you simply want to create content. So touch does so without using any bytes, with the exception of metadata-related byte information. So that's a touch command. Other commands, cat. Well, really what this does is catenates or concatenates content. So i.e. aggregates various files into, let's say, one output stream. And it is linear. So as you supply the files, so are the data interpreted and represented. Let's see what's happening to our file here. Let's actually fade it to the background. So let's see what we're doing here. Let's see where we currently are. 3rd minute. So let's do a touch test.txt. And now you see it's been updated in the 3rd minute of the 8th hour as opposed to the 2nd minute. So touch updates that property if the file already exists. And again, 0 bytes is nothing in the file, but it still updates it if it doesn't exist. And creates it, well, updates it if it exists and creates it if it doesn't exist. So now cat. So now you've got content. Well, let's see, what sort of content? Let's echo some content. So let's echo 1 into 1.txt. And echo 2 into 2.txt. And finish that up with an echo of 3 into 3.txt. And finish that up with an LSL. So now we've got these disparate files with disparate content. Now cat will take the files as they're specified, let's say 1.txt, 2.txt, 3.txt, and by linear we mean 1 is specified before 2 is specified before 3. So as they're specified, they're read and regurgitated. So as we cat, the contents are displayed, well, read and displayed in a linear fashion. Now that you have this linear stream from 3 sources, you can concatenate them or aggregate them or converge them to a single output stream, which potentially could be placed in a file or sent somewhere. So perhaps the contents of these 3 files should be condensed or collapsed into one file. So for example, cat 1.txt, 2.txt, 3.txt aggregates the 3 files into one linear output stream. So once you've done that, you modify it accordingly. And let's say your new output stream looks something like 1 through 3.txt. And that'll create a new file for you. So let's take this and create that, and let's take a look. So now when we cat 13.text, it has all of the output from 1.text, 2.text, 3.text in one file. That's simple. These are rudimentary examples of unimportant garbage data, but it still illustrates the concept of being able to aggregate content from disparate sources linearly and streaming them to something new, such as this new file called 1.1-3.text or 1 through 3.text, which means you can apply it to important data, aggregating them accordingly and placing them into some sort of target linearly. So that's the whole idea behind cat. Cat can also be used to reveal the hidden content in files, such as the codes associated in files. Sometimes files become corrupt during transmissions and so on, and cat can be used to expose those codes. Just run a cat help, you'll see the various options that may be used, and you can show the non-printing characters using cat v, for example, so 1.3 text, and it'll, if there are any non-printing values, hidden characters, etc., it can dump that data for you. Sometimes it's useful, sometimes you have problems with a file, etc. Sometimes you want to see where things are delimited. You can use the E option. That shows you sometimes there's space in places that you didn't expect spaces to be, causing, say, problems with your content, and so on. So use cat to ascertain that information as needed. Now you've already seen make directory. Obviously that's used to make directories. So make directory creates directory. Of course, providing permissions are appropriate or correct, and so on and so forth. What about removing directories? Well, remove directory, followed by directory removes the directory recursively. This is a command you have to be careful with, especially as root, obviously. So if you want to get rid of the whole temp tree, remove rf temp, and it's gone. That's it. There's no bringing it back. There is no recycle bin. This isn't Mac OS X, where there's an artificial recycle bin brought to you by Mac OS X. On a standard Nix system, Linux system, Solaris, etc., if you delete something using remove rf or remove directory, it's gone. There's no recovering unless you use special tools. Well, unless you cease what you're doing as quickly as possible and use special tools to recover that lost data. And similarly, remove rf removes content recursively. And obviously be careful with these. So be careful, as these, let's say, tend to be generally, let's just put generally between quotes, because you can still recover if you are careful, but tend to be generally unrecoverable. So keep that in mind. So, tons of other commands. Well, we've used echo. Echo just echoes whatever. Echo dumps whatever you tell it to either stand it out or file or elsewhere. And that can be useful. Sometimes you just want to send some text or a stream of text somewhere. So that's what you use echo for. Some other commands that are of interest to us. History dumps a history of recently executed commands. Now each user maintains a history, so let's just note that this is per user base. Each user maintains a distinct history, so you need privileges to be able to view a given user's history. So history alone reveals the history of commands that you've executed. And they're indexed beginning with 1, and any of the commands may be referenced using exclamation mark followed by the number associated with the command. So each command is indexed, let's say beginning with 1, and can be referenced basically using exclamation and the number. So basically IE exclamation 50 executes command number 50 from your history. And the shell maintains a history. Per user, the history is maintained. If you take a look in your home directory, using the hidden option A, there are a series of files, that are bash related. Bash underscore history is the file that contains your history. So IE LSL LA, that is home directory, bash underscore history. And this contains your history. And it may be modified to store as many commands as you want, and so on and so forth. Speaking of how many, let's say, lines or entries are in something, that brings up another command, WC. By itself, it counts words, but it's probably more often used with the L option, as this counts lines. And in Nix, we're always concerned with textual data and the number of lines in something, as it gives us a sense as to perhaps how busy or how much information is flowing through a given facility, let's say your web server, your database server, and so on. So WCL bash underscore history reveals there are 39 commands stored. Now there's a discrepancy between what's stored in the bash history file and what you find in history, because these values are stored in memory, and when the shell is closed, the differences are committed to the history file. And because we may have these shells open, not indefinitely, but for long periods of time, without syncing the differences that are stored in memory, in the internal memory as opposed to on disk, there will be discrepancies. Now, usually by default, you can store up to 1,000 commands. So 87's in memory, 39's on file, and as we close these out, things will be synchronized. The differences will be synchronized accordingly. And of course, the more shells you have open, the different commands you run, the more synchronization is necessary, and the more likely there are discrepancies between the buffered history and the file or disk base history. So expect that to be an issue. Now, we've been using the greater than symbol, which really is just an alias for redirection. So greater than symbol. This is basically output redirection in clobber mode. And clobber mode basically means erases any target indicated. So you have to be careful with this option. So when we cat the contents earlier to a new file, we were using output redirection mode and clobber mode. So let's say catting the contents of this basically uses output redirection in clobber mode, because essentially cat aggregates the contents of these three files, and then the operating system is told to clobber the target file. So if it exists, it wipes it. So let's see. Let's re-execute item number 72. So what did that just do? Well, there we have the three files. And now if we re-execute item 74, this will clobber 1 through 3.txt. But it didn't exist. So if it doesn't exist, it creates it. And if it exists, it overwrites it. So if we repeat that particular process, instead of ending up with 12 bytes, we will see 6 bytes. LSL, and it's 6 bytes again because the file was clobbered. Now the opposite of that is append redirection. This is append redirection. So if content exists, add, else, create. That's the option you want in the event that you need a cautious approach to dealing with your content. So just change from a single greater than symbol to double greater than symbols. But be careful with this, because if your source files are large, and this was not your intention to append, but rather to clobber, then you could end up duplicating your data, which could easily exhaust your storage. So in this example, the file will grow from 6 bytes to double that. That's LSL, and there you see, because this is append redirection. So it saw that the content existed, 1, 2, 3, and simply added, beginning with a new line. So that's the difference between append redirection. But if a file doesn't exist, it simply creates it. So remove rf 1, 3, followed by the same command we just executed. And now you'll see it's 6 bytes, because it doesn't, or it didn't exist. And so long as it exists, it will simply add to the file. That's append redirection. Another facility that's of importance is command chaining. So we can chain commands using a variety of symbols. This performs command chaining using logical AND. So basically, the preceding command needs to succeed in order for the current command to succeed. So let's say we cat something into this file, and then if it succeeds, we do LSL. So the only way this will work, meaning the LSL, the second command, is if the first command ran, or the only way the right command will execute is if the left command executed. So we see LSL's output because cat worked. And to break that, let's say we cat something that doesn't exist, 12.text. Well, because 12.text doesn't exist, it caused cat to fail, which then means the logical ending broke down, which means ls couldn't run. That's logical ending, and you can string this together as much as you need for all the commands you need. So if you have 10 commands that should run in a logically ANDed fashion, this is the facility to use. Similarly, you have logical ORing. So this is command chaining using logical OR. So you execute a series of commands, and it's one or the other. So let's see what happens here. So we change the AND to OR. So basically, it's left or right in this example. If the left is successful, we don't need the right. If the left fails, do the right. So because the left will succeed, we won't see the LSL. No LSL. But rest assured, 1.3 text is now larger than before. That's logical ORing. It's one or the other. And if we break it, let's say we try to cat something that doesn't exist. Let's say 12.text. Well, fails. So the logical OR instructed the right command, LSL, to run. That's logical ORing. And we'll continue studying our basic commands next.